you here tonight. Bear with me. I can't see you all, so at least that is something. So tonight we are thinking about fractions. Deep joy, I hear you all call. So let me just work out how to change my slide. Oh, here we go. Okay, so our objectives tonight. So we'll be having a little look at what some research tells us about fractions, and think about why so many people find fractions and by its nature, decimals and percentages tricky to understand. We'll think about the underlying concepts that need to be secure, which is a major reason why people don't understand. We'll be thinking about what a fraction actually is, some of the language difficulties, especially for our dyslexic pupils, a few teaching ideas for both at home and maybe in a more formal setting. We'll be thinking about some of the manipulatives, or either in person, concrete, or online. And there are some resources and references at the end. So I'm going to start with some interesting research, because I think this puts it into sort of context of why people find fractions difficult. So back in 2013, the University of Cambridge did a study on adult volunteers and found that only half could really correctly decide if pairs of fractions represented the same magnitude. So did 2/4 and 4/6, were they the same or not? So this was adults. And these researchers did a study of 13, 14-year-old eighth graders in America. And they did this in 1978, so quite a few years ago now. And they found that just 24%, so nearly a quarter of these 13 to 14-year-olds could correctly answer what's the nearest whole number to 12/13 and 7/8. And they were given the choice of either 1 to 19, 21, or I don't know. But then they repeated this in 2014. And what percent do you think were able to give the correct answer of 2? So bearing in mind, 1978 was a long time ago. We would hope that maths teaching has improved in the meantime. Well, the answer was actually it had only gone up to 27%, which, you know, in 35 years of teaching, that's actually not a particularly huge improvement. And why might that be? Well, some more research here done in 2010 posed some word questions, and they asked, you know, they asked teachers, do you need fractions with multiplication or division to solve this? The US teachers, about a third of them got it right, as opposed to in Taiwan, where nearly 3/4 would get that answer right. So fractions are really tricky, and lots of people find them really tricky, and perhaps the way we teach them in the West doesn't help either, whereas in the East, and of course teachers probably study for longer in those areas. Okay, so why are they so hard? Well, we've got notations that we need to interpret. They can look weird. We don't really know what's going on. And the size or magnitude of a fraction, it's actually a ratio of the two numbers. It's not just like reading a number and knowing what it is. You've got to work out how the two numbers are connected. And there are more rules and procedures for fractions than for any other concept in Key Stage 2 or Key Stage 3. So until you start doing your GCSE and your higher level maths, there isn't another subject which has more rules and procedures, which again can make it all very difficult. And some of the research also says that when we the understanding of the rules when we're working with fractions and decimals are actually beyond what children conceptually understand when we first teach it. So no wonder they don't really get it, because it's actually, for a lot of children, beyond their knowledge. And to understand fractions, you really do have to be able to reorganize your understanding of numbers. And again, this research shows that only just about half had done this by year 6, year 7, when in theory we're doing lots of manipulation with fractions. Okay, and for our learners with SPLDs, well, you need really good working memory, because you're going to have lots of steps, lots of procedures, lots of things to do. You've got to keep track of stuff, all which will use up working memory resources. You've got to be able to look at the numbers of fractions and decimals and not treat them like whole numbers, which can be really hard to inhibit that process. And during all of these difficult things, we've also got to sustain our attention. And these executive functions of working memory, inhibiting and sustaining attention, these are all the things that people with SPLDs are going to find more tricky, because that's the nature of an SPLD, that these things are tricky. So it makes, when you take away from the actual fractions, all of these things make it much, much harder for us to learn. And so why are they hard? Well, many people are only taught at abstract level. So we're just doing things on paper, writing down numbers, putting lines, manipulating them, and we're being taught lots of rules. So we have things like, well, the bigger the bottom number, the smaller the fraction, which works sometimes, but doesn't always. We have things like, well, if you're going to divide fractions, let's remember our mantra: keep it, change it, flip it. It doesn't actually help with the understanding of what we're doing. And again, for our learners who can't remember lots of processes, it's very easy to get muddled up. Other reasons why they're a nightmare: the language is an absolute nightmare. So half, many children have a notion of half in everyday life, but they may not represent it as 2 parts. So they can kind of say something's been divided, but they won't specifically know that it's 2 parts. And likewise with quarters, there's no notion of the 4 in quarters, unless you know your Latin. Then in a busy classroom, we're talking about things like 10 or 10th. They sound so similar, and again, for our dyslexic learners in particular, hearing the difference in between those can be really tricky. And I know from experience, when I'm working with older students, sort of key stage 3, key stage 4, is we look at place value, and often if they've been working with fractions, they'll read the 10 column as the 10th column and vice versa. Well, a 10 and a 10th are 100 times bigger and smaller than each other. So we do need to know. And likewise with 100 or 100th, they're 10,000 times difference in size. So if you miss the at the end with 100th, you're thinking of something that's massively different. And again, the language, 6 7s, or did you say 6 7ths? Or do we even mean 67? All of these values are completely different and really easy to muddle up. And then we have other fractional language like 0.5 and 50%, which a lot of students don't even know that that's anything to do with fractions. So what can we do to help? With all students, I would say over-exaggerate stick your tongue out, get them to stick their tongue out, a bit like you did when they were learning the sound in phonics, to really make sure that they know what they're saying and you know what they're saying as well, so that you really need to be able to hear, and then they will hear the difference between them. Again, talk about the word half. Why isn't it 1 tooth? or why isn't it 1 second, which would seem more logical to bring in that number 2. And another thing that we do is, well, I'm saying a here, but actually we kind of go a half or a quarter, when actually we mean 1, but we don't say it's the number 1. We're just kind of assuming that the students will know that we mean 1 when we say And what I find quite successful with often younger students is just to use the American vocab and use the word fourths instead of quarters. I always used to do a play on that. The Queen was very posh and would say quarters, and the Americans would just say fourths in their best American accent. But if it helps cement the number to the language, that's all useful. And of course, another reason fractions are tricky is because they can have many, many meanings. So we have our fraction there written. A lot of students will say, well, that says 2/3. It does indeed, but that doesn't really tell you that much about it. Some might say, well, it means 2/3. And it can well do. It can mean you have 3 things and you're thinking of 2 of them. It can also mean 2/3, and we might think of this sort of picture that might help us think of 2/3, or it could be 2/3 of something. So again, another image where we have 2/3 dark blue and 1/3 is grey. But it can also mean, and does also mean, 2 shared into 3. It's completely different, a completely different meaning, but it is still all represented by the same fraction. And of course, it can be a position on a number line. So it's going to be that way along, 2/3 of the way between 0 and 1. And what we often try and do is try and think about one of these ideas for fractions, and we don't think about understand that we have to learn fractions in lots and lots of different contexts in order to have a true understanding of it. So the knowledge that we need to understand fractions. So this is like a wall of knowledge that we're building up here. So the first thing we need to understand is that numbers can be split into equal and unequal bits. So 5 could be just 5, it could be 3 and 2, it could be 4 and 1. We need to know that we can do that with numbers. We can split them apart as we need to. We also need to understand equivalence. So 12 could look like 10 plus 2, or 15 minus 3, or it could look like 2 6s, or 48 divided by 4. It could look like lots of things, but the value is still 12. And so we do need to understand equivalence as more than an equal sign. It doesn't just mean the answer. We need to really understand that things can look different, but mathematically they're going to have the same value. And then the thing that's kind of quite hard to get your head around with fractions, and yet in everyday life, it's something that's quite obvious. So that if you have something, whatever it is, whether it be this chocolate bar here or something else, and you split it into more pieces, then each piece will be smaller. There will be more of them. Before you had one big chocolate bar, now you have lots and lots of pieces which are smaller, but the amount of chocolate hasn't changed. And then the other major understanding we need is that conceptual understanding of multiplication and division, because until we have all of these in place, it's going to be really, really difficult to understand fractions in any meaningful way. We need to get all these building blocks in place first. So what can we do to help in our homes? Just, do sharing into equal and unequal groups. I think sharing equally comes in a way quite easy to children, and they might find it hard to share into unequal groups, but sometimes we do. And you want to link that language, so use the language of division and fractions in your everyday thing. So when you're splitting your pizza between 3 of you, you're cutting it into thirds, you're just using that language on a daily basis, so that it becomes part of the sort of the background, and that over time the children will understand. Again, the little squares in a bar of chocolate are perfect for all things fractions. So if you've got some fractions homework, your bar of chocolate with some little squares in it of either 12 or 16 squares are probably going to cover you for most things, and it'll make it far more palatable. And so again, like I said, if there's 5 of us, we need to split this cake or this bag of M&Ms into fifths. How are we going to do that? And of course, if you've made the cake and it's time and there's 4 of you, and you might say, well, we are going to split this into quarters, but actually I've put in all the work, so maybe I need to do more. So I'm going to split it into 5 bits and I'm going to have 2/5 of it. I'm sure that will get people running to maybe help do a bit of washing up or something so that they can have a bigger fraction. Okay, so ideas. The best thing I have found is small pieces of paper. This is, as you can see, stuff with a hole in it because it's just meant to go by telephone. So garden centres are brilliant for selling all these little pads of paper, quite cheap. And I find these absolutely brilliant for looking at fractions. So you can start with your piece of paper, get them to fold it in half. First of all, how do we know it's in half? So they're going to be equal. You can fold it so it's not in half. So if they're only talking about 2 pieces, you fold it so it's not in half, so that they're having to really think about what makes it a half, 2 equal pieces. And then, well, if we open it up, how many pieces are we going to have? Most children will know that once opened up, there will be 2 pieces. But then we're going to fold it again. If we fold it again, how many pieces are there going to be? Some students will say 3, but again, most will say 4 because they've generally had experience of that. And then you keep going. After 4, it gets a bit trickier. An awful lot of children, after when you fold it for the 3rd time, I have a piece here that has been folded for the 3rd time, they will predict that there's going to be 6 pieces because they're thinking, well, it was 2, it was 4, it's going up in 2s, there's going to be 6. But when you open it up, of course, there is going to be 8 pieces, which you may not be able to see very well there with this, but there are 8 pieces. And then they're going to think about, well, why is that? And then they're going to fold it up again and fold it in half again. And you kind of keep going until they can predict how many pieces there is going to be. Because after 8, we'll often get 10 rather than the 16 that there are going to be. So, and it doesn't matter if they make errors, because if you've got a pad of paper, it's all the same size. There's lots of it. You can just throw away a piece and start again. It's not the end of the world. And so once you've done that, you can then be looking, well, how many quarters are hiding in a half? And we can see them there. We can label them all up and we can see what's there. And the other reason I like square paper is because if we fold this in half and we've decided this is a half, so we might have written on it that it's a half. We then take the same size piece of paper, but this time we fold it into triangles. And we say, well, what's this? Oh, it's a half. Okay, so what's bigger? Is this bigger? Which half is bigger? And they don't look the same at all. But if you have the understanding of a half, you know that they must be the same size. And that's just a really good way of seeing the visual that they must be, you can use that reasoning, they must be the same, even though they look completely different. And then once you've done quite a bit of folding, you can then be labeling. So I've labeled, disappeared, all of these labeled an eighth, because there's eight of them, or our quarters are labeled as a quarters. They can then cut out a quarter and cut out an eighth and actually look, which one's bigger? Why is it bigger? This has got an 8. Why is it smaller than this one? And you can do all of those sorts of things. And the other thing that you can do is when you've cut out your quarter, you can say, well, what have we got left then? And again, using that reasoning, oh, well, we had 4 quarters, we must have 3 quarters left. We've cut out 1/8, we must have 7/8 left. But which one's going to be bigger, 3 quarters or 7/8? And it's all about building in that reasoning, but they just need lots and lots of practice. They won't get it once. You won't do it once and they'll get it. They'll probably need to do it several times, lots of times. But if you've got lots of paper, it can be done. Okay, so conceptual understanding of multiplication and division. I'm not going to labour on this, but multiplication. Most children will read that as 3 times 2 or 2 times 3. And for division, 6 divided by 2 and 6 divided by 3. But what does that mean? That kind of just tells us we can read numbers and we can use the right words we've been given. How can we explain those without using the words times? So here we can see we have 2 lots of 3. We can also see that we have 6 shared into 2 equal groups. Or we could say, how many 3s are in 6? So 2 multiplied by 3 does give us this picture, but both of those divisions also go with that same one picture. And at the bottom one here, we have 3 lots of 2. That is also 6, but we can kind of see it's a bit different. We've got 3 lots of 2 this time. We haven't got 2 lots of 3. But we can still see 6 divided by 2, because how many 2s are there in 6? Or we can see 6 divided by 3. Let's share 6 into 3 equal groups. Division is incredibly difficult for children to understand, but until they can really think about it in both a sharing and grouping, it's going to make fraction work much more tricky. So what is a fraction? Well, it's a relative amount, which again makes it much more difficult. If I said to you, are you taller than, and then didn't finish the rest of my sentence, it wouldn't make sense. In the same way, a fraction doesn't make sense unless you know what you're comparing it to. If it's a half, it has to be a half of something. It doesn't exist by itself. But of course, we're often given fractions by themselves with no context. So we're then expected to know that if the context hasn't been given, then a fraction, what we mean is a fraction of 1. What is the fraction of 1? What is half of 1? What is a quarter of 1? But we don't say that. We just say a half, a quarter. We don't give the thing that we're comparing to, which is 1, if it's not a word problem. And again, the size of a fraction is actually how the 2 numbers, it's the ratio between the 2 numbers. It's how they work together with multiplication between them. So just a recap on vocabulary then. So key vocabulary for fractions. So our bottom number is a denominator. I know I heard of one teacher who actually always said denominator in a very low voice to indicate it was the low part of the fraction. And that's telling us how many pieces make up the whole. So here we've got 4/4, or we've got 4 jumps on a number line to 1. And then we have our top number, which would then be the numerator. So we do that in a much higher voice to indicate that it's a number above the fraction line. And that's telling us how many pieces we're thinking about. So in this case, we're thinking about 3 out of those 4 pieces. We're thinking about 3/4. Unit fractions is another bit of vocabulary you might hear. Unit fractions just means that the numerator is 1. It's a fraction with a 1 at the top. So 1/3, 1/4, 1/5, etc. Improper fractions. So these are fractions that are bigger than 1, but our denominator is still telling us that each bit is a quarter. But in this case, we've got 5/4. So we must have more than 1 whole. In this case, we're at 1 1/4 on a number line. And if we want to say it with reference to whole numbers, then we would say it as 1 1/4. So when it's a mixed number, we're using different ways of describing, so we have to keep the two parts separate. Whereas with the improper fraction, we're just saying how many bits have we got of what size all together. But we can see there that with the 2 bars there making one nice big equal sign, that the 2 of these are in fact equivalent to each other. Again, they're different ways of saying the whole thing. So thinking about equivalent fractions, there are lots and lots of terms for this. So you might hear cancelling down, simplify, express in its lowest terms, in its simplest form. All it actually means is that we're taking lots of little pieces and we're seeing if we can put them together to make fewer, bigger pieces. Again, it's sort of counterintuitive, and it is actually easier when we're thinking about equivalent fractions to go back to the paper folding and to actually do it the other way first, so that you start with a whole, then you end up with halves, then quarters, by keep chopping things up, making them smaller. But when we're simplifying, we're doing it the opposite way round. So here we have 15/20. So we have 20 little squares and 15 of them are purple. So we have 15/20. This will cancel down, simplify to 3/4. So all we're doing is we're taking those 20 pieces and we're saying, can we actually put them into bigger pieces, but still keep the same proportion, the same colours? So here we've still got 3 purple and we've got 1 yellow, and we can see that they're identical in size. Nothing has changed apart from the fact that we have made some of them bigger pieces. And when it comes to doing this on paper, we're looking for things that both numbers can divide by to work out what our new fraction would be. So in this case, we would divide both 15 and 20 by 5, and that will get us to our new fraction of 3/4. But for those of us in Key Stage 3 and beyond, not really suitable for younger children because they won't have done prime factors yet. But once the children have done prime factors, usually in year 7, it then can make cancelling down much easier, because one of the problems is we're looking at this and we're thinking, well, I don't know what goes into 18 and 51, and we're going to have to go through our times tables and it's all going to get very complicated. There's going to be lots to do. But if we've done our prime factors, we know that we can split 18 Well, it's an even number, so we can split it into half, so we can split it into 9 times 2. I know that 2 is a prime number, so I don't have to worry about that one anymore, but 9 isn't. But I can split that further into 3 times 3. So I have broken my 18 down into its prime factors. Now I can do the same thing with the 51, but 51, it's not in the 2 times table. That could be quite tricky. But will it be in the 3 times table? Well, a really good little trick there is to add the 2 digits. So I'm going to add the 5 and the 1. That gives me a total of 6. 6 is in the 3 times table. Therefore, it is going to be a factor of 3. So 3 is going to be one of its factors. And that is a prime number. So I don't have to worry about that. But now I need to work out how many 3s are in 51. Well, let's think about what we know. We know that 3 10s are 30. So that's going to leave me 21 to go. And if I know that 3 7s are 21, then I must know that there are 17 lots of 3 in 51. And so now I've got my prime factors. I can rewrite my fraction. So instead of 18 as a numerator, I'm going to write 3 times 3 times 2. And for the denominator, I'm going to write 3 times 17. Now this is helpful because I know that 3 divided by 3 is now 1. That's something I know. And what am I left with? I'm now left with at the top, 3 times 2 is 6. And 17 is all that's left on the bottom. So I've simplified that fraction by using prime factors. And the fact that you can do it in separate bits just makes life so much easier once you know how to use prime factors. Like I say, probably not any good for Key Stage 2 because they won't have done prime factors yet, but a really useful way for older children. And they like it because they can generally do prime factors. So coming on to the 4 operations then, adding and subtracting fractions. So we're starting off with 1/4 plus 2/8. Okay, so the problem with adding fractions is that 1/4 is a different size to 1/8. And if we've already investigated that, or we're doing it again, it's really useful to know. So we need to know, we know the different sizes. And the analogy here really is if you think about column addition or column subtraction, you can't add the 7 that's in the 10s column to the 2 that's in the 1s column and get any meaningful answer of 9, because you've got 7 lots of 10, you've got 2 lots of 1. They're completely different. And it's the same with fractions. We can actually only add things which are the same size. Normally, that size when we're using numbers is 1. So when we say 5, we mean 5 ones. So 5 add 2 is 7 because 5 ones and 2 ones make 7 ones. So when we're coming to fractions, we've got to make them the same size. So here we've got 1/4 and we've got 2/8. Well, if we've done a lot of paper folding, we can either decide, well, I know that 2/8 is the same as 1/4, so I'm going to swap out my 2/8 for 1/4, and then I've got 2 things the same. Or we could do it the other way round. We can take our 1/4 and say, well, I know that's the same as 2/8, and then we've got 2/8 plus 2/8. But because we can then see halfway across, we are can then cancel that down for it and replace it with a half, because a half will go twice between there. So our fraction there is a half. So when we're looking at this, we can't make thirds into quarters easily. So what we're having to do now is we're having to think, okay, we need to break these into smaller parts. So I could break my quarters in half. That would give me 8 pieces, but that's still not going to help with my thirds. I could split my thirds in half and make 6 pieces, but that's not going to help either. So we need to find something where we're both going to go in. And in this case, we know that if we split 4 into 3 pieces, it's going to give us the same result if we split 3 into 4 pieces. So we've got 4 and 3 there. When they multiply together, they're going to give us 12. So we can see that a quarter is indeed going to be 3/12, and a third is going to be 4/12. And when we add all of those together, we can see we're nearly at a whole one, but not quite. And so the thing also that I've forgotten to say beforehand is that you really want to be predicting how big is this going to be? Is it going to be bigger than a whole one? Is it going to be bigger than a half or more than a half? We want to be doing that as we go along. And so our fraction there is 11/12. Similarly on this one, so this time we have 2/3 minus a quarter. Again, we know that we're going to have 12ths, but again, it's worth predicting how big is it going to be? And because we're subtracting, we also know that we can look at, instead of subtracting, we could think, well, what do I need to add to 1/4 to get to 2/3? What's that gap? What do I need to add? Again, we know it's going to be 12, and we can add 5/12 there in order to get to our answer, because the gap there is 5/12. So when it comes to multiplying and dividing, this is where all the rules really start. And then people get very confused about what the rules are meaning. So we're looking at this brickwork again. And we should always try and start with something that we can intuitively do. So if we can start with something we already know how to do, that's going to set the scene for what we're doing. So we're going to start with whole numbers. So what does 4 times 2 mean? Well, it means 4 lots of 2 or 2 lots of 4. That we need to understand that first. That's our first layer of the brick. Then we might just change one of those numbers to be in a fraction. 1/2 times 4. What does that mean? Well, it could mean a half lot of 4. So we've got 4 apples, it could mean half of it. Or it could mean 4 lots of a half. So we have 4 half apples. Either way, we're going to end up with 2 apples. But being able to switch between different representations just makes your life easier with fractions. It just makes it much, much easier. So then we get to, well, what does a half times a quarter mean? It either means half of a quarter. So we go back to our quarters and we can think, oh, well, half of that, if I split that in half, I'm going to have 8 bits. It would be an 8th. Or we could have our half and we could work out what's a quarter of that. If we split that into quarters, again, we're going to have 8 parts. And so we end up either way with a half of a quarter is an 8th. But by doing it with something concrete first, it just helps us get through that language barrier. And likewise, we could do this with bar modeling. So 2/3 of 1/4. So we've got a quarter here. I know it's a quarter because my square is representing the whole, and I've got a quarter of it is yellow. But I only want 2/3 of that. So that means I need to split that now into thirds. And so I can see if I split that 1/4 at the top into thirds, then I'm only going to be looking at 2 of them. So I've just got 2 little pieces there. Or we could look at it as 1/4 of 2/3. So we can look at thirds. And as an aside, if you're folding paper to get thirds, be prepared to use loads and loads and loads of paper, because most children will just keep folding it in half. And as soon as you fold it in half, you can't get thirds. So that's just another aside. But yeah, I get through lots and lots of paper trying to get understanding thirds. So we've got our paper divided into thirds, and then we're going to divide each of those thirds into a quarter. And we can see again that 1/4 of each of those 2/3 is also going to give us 2 out of those 12 squares that are already there. And it doesn't matter which way round we're doing it, because we're still going to have to simplify that. And we can see that if we lump everything into 2s, we're going to actually end up with 1/6 at the end of the process, because we can make those bigger pieces. And if we have bigger pieces and there's less of them, they're easier to handle rather than lots and lots of tiny pieces, which is why it's called simplifying, even though it doesn't feel very simple. And we know what the answer to this is, but we can show it as bar modeling as well. So we can show 1/4 of 2/3. So we've got 2/3 there, splitting it into quarters. Each piece is going to be worth 1/6. Or we can have 2/3 of 1/4. So we've started with 1/4. We've split it into 3 pieces. That's going to be 2/12, because we would need 12 of those to get all the way to being a whole one. But we can again simplify that to 1/6, so we can see why that would happen. Okay, so the trickiness then is dividing fractions. Okay, so as with the other, we're going to start with whole numbers. So 6 divided by 2 means 6 split into 2 equal groups, or how many 2s are in 6, or 6 is 2 lots of what? So we got 3 different ways of thinking about even a whole number division. So we're either splitting 6 into 2 equal groups, each group is 3, or we're working out how many 2s are in 6, or 6 is 2 lots of what. Once we've got our head around that, we can then look at dividing with whole numbers, but having the smaller number first, which is eminently possible, even though a lot of children will tell you it's not, but it is. So what does 2 divided by 6 mean? It means 2 split into 6 equal groups, or how many 6s are there in 2? Not particularly helpful. The how many is only really helpful if your second number is smaller than your first number, or 2 is 6 lots of what. So we've got 2 here, and we've split it into 6 equal bits. So 1 must be split into 3 equal bits, therefore it must be 1/3. Each piece is 1/3. Or on the number line again, we have 2, and it's been split into 6 equal jumps. So 2 divided by 6 is a 1/3. So therefore, once we've looked at whole numbers, we can then change one of the numbers into a fraction. So how many halves are in 6? Well, we can see that if we've got jumps of a half, there are going to be 12 of them in 6. Or we could say 6 is half of what? So we could use that language. We've got a number. We know 6 is half of it. What's the number? So 6 divided by half is 12. So you can see how it's the language that builds all the time with these. And then we have a half divided by 6. So split a half into 6 equal pieces. So are they going to be big or little? Or half is 6 of what? Again, it can be hard to think about, but we've got a half there. We're going to split it into 6 equal pieces, and therefore there must be 12 equal pieces. Each piece must be 1/12. And once we've done that, we can then get into these horrible ones where we've got a half divided by a 6th. So how many 6ths are in 1/2? Okay, so if we've got an understanding of 6 and halves, that actually isn't too bad. How many halves? How many 6ths are in a half? Well, I can see that there are 3. Or half is 1/6 of what? So if we've got 1/6, that means we've got 6 jumps. Each one is a half. Therefore, our answer is 3. Okay, and then the final way round, 1/6 divided by half. How many halves are in 1/6? That's quite hard to think about, because obviously a 6th is smaller than a half. Or 1/6 is half of what? I think by changing that language around, it's much easier to get your head around. So 1/6 is half of what? Well, it must be half of a third. Okay, I realize that we are beginning to run out of time, so I'm going to just quickly whiz through the word problems. So a list here. So again, I like to use post-it notes or bar models to work out the problem. We add the words, match the numbers, and work out, remind ourselves of what we're asked, what is the answer, and then we can solve it. So in this question, 3/4 of the people in a school are students. There are 150 students. How many people are there? Okay, so we've been given 3/4. So we've got to work out the missing fractions. The missing fraction, well, I know that if there are quarters, there are going to be 4 bits altogether, hence the 4 little post-it notes. 3 of them are what we're thinking about. So there has to be 1 bit left, because I know that 3/4 and 1/4 are going to make 4/4. Then I'm going to add the words. So I know that the 3/4 in this question are students. So these have to not be students, and therefore everything else is the students and the people who aren't students, all the people together. So I've kind of taken that language and put it into something that makes a little bit more sense. Now I can match the number to the bit I'm told. I'm told that there are 150 students. So how's this going to help me? Well, I can see that our students have been divided into 3 equal bits. So those 150 students must fit equally into those 3 pieces. And crucially, the other 1/4 that's left will also have to be the same size. And for this question, the answer that we want is the top bit, the students and not the students. And in this case, it would be 200, because there'll be 50 in each box. Whereas a similar question, we're going to have 3/4 of the people in the school are students, but this time 150 people are not students. So again, we're going to put our language in. So we got our students, our not students, but this time 150 are not students. We still want to know how many there are altogether, but if there's 150 in that box, then there must be 150 in all the other boxes, giving us our answer of 600. And then lastly, again, a similar question. So I'm doing the variation theory here, where you keep lots of things the same, but alter some of it, so that it really focuses attention on what's changing. If you use different fractions, it takes away from what's the same. So again, we're looking at the students and the not students. This time we know that the 1500 is everybody, and there's 4 equal pieces. So those 1500 must be divided equally. But this time we want the students for the answer. So we're going to have 3 of those 4 boxes, which is going to give us 325, except for it's not going to give us 325. It's going to be 325 times 3. So there we go, a wrong answer there. Likewise, these are often tricky ones for older children. So everything is reduced by a quarter. What did the t-shirt originally cost? Well, if it was reduced by a quarter, then what I paid was only 3/4 of it. So it's working out what fraction. The original cost was where we started. What I paid was the £24. I'm trying to find out the original cost. Therefore, the £24 divided by 3 gives us 8 in each box, and we got 4 lots of 8. And similarly there, we're being asked, what did the t-shirt cost last year? This time I paid £24, but a quarter of that is off, which is this time only £6 to come off, therefore £18 to be left. And I am going to leave it there. I think I did have a couple of slides on decimals and fractions. Decimals are just fractions with a denominator of 10 or a multiple of 10, hence y. And 0.25 a quarter is just into hundredths, and percentages are just fractions with a decimal with a place of 100. So, and often they're taught decimals and percentages are not taught alongside fractions. And there we go. There are resources. There are free. Let me just click through this. So there we go, some slides there on how to order. There are some resources coming to you, so some top trump games, 3 levels. There is both as Word and PDF files, so you can change them. There are some paw print tokens, the idea being that you can either win tokens rather than just winning cards, but also if you're trying to work out a quarter of 12, if you've got 12 tokens, you can then physically use those to work out what a quarter of something would be. You can split them into the right amount. So the green are just unit fractions, blue are unit fractions, but of different amounts. So it kind of builds up, and yellow are just proper fractions. And some books there, some online resources, which can be useful. And in one slide, what we've done. Why is it hard? Because they are hard. We need to understand multiplication and division, the language difficulties, teaching, and some ideas. There we go. Bit of a rush through at the end. Sorry about that. Are we?
Thanks so much, Amanda. Sorry, it wouldn't let me put my screen back on. Thank you so much. I know we spoke earlier and you had so much detail to get through, and which is fantastic. But just a reminder that we are sending Amanda's amazing slides and the recording. So if you want to go back and look at it, or look at some of the other slides that Amanda was hoping to be able to fit in tonight, then please do take a look. We have run out of time, so we won't be able to do questions, but I'm sure Amanda won't mind if anybody has any really dying questions that they would like some advice on or anything. If you do email us at events@PDA, then we can pass them. Oh, actually, Amanda's put it on a slide, so that she's actually letting the floodgates open now. So if anybody does have a burning question that we didn't get a chance to get to, then please just reach out to us or Amanda, and I'm sure she'll be happy to help. So yes, it just leaves me to just say thank you so much, everybody, for joining us. Thank you, Amanda. It was absolutely brilliant. You have an amazing way of making it sound so simple. and I know some things, just even like I have a dyslexic daughter who is fine with times tables, but the minute you flip it around and try to talk about how to divide something, even though it's exactly the same equation, just the other way around, it just does baffle her. So that's some great tips there that I'm going to try with her tomorrow after school. So that's fantastic. Thank you.
I'm sure she'll be very happy.
Yeah, sure. She actually doesn't mind the math side of things as much as the literary side. So yeah, okay. That's good. That's fantastic. Thank you so much. And just a reminder that we do run lots of free webinars, so do check out our website. And that actually on the week beginning the 2nd of October, we've got Dyslexic Awareness Week, which several evenings that week we're running free webinars for all different age groups. So the best thing to do is just to go onto the website, and all the events are listed there. They're all free. You just register like you did tonight. And I think that's all really. Apart from to say thank you so much to Text Help, who have sponsored this series. It's been fantastic, and we really, really appreciate it, and all the support that we get. And that's it. I think we have run over, so I will let everybody go. Thank you, Amanda. Your expertise has been fantastic, and thanks to the team behind this as well. Thank you. Good night, everybody.